Alright, welcome to Lab 5, which is the lab over magnetic braking by applying Faraday's law. So the purpose of this lab is to collect time data of a falling magnet through a aluminum foil tube to understand Faraday's law and generate a computational model of this law. Some key ideas that we're going to be using are the magnetic field of a bar magnet, also known as a dipole, magnetic flux, and the time derivative of this value in order to determine EMF and then current. And then gravitational force, Faraday's law, Ohm's law, and Lenz's law, as well as some momentum properties. Oh, those are all, to the right are all the formulas that you're going to need for this lab too, in order to actually run the calculations and set up your model correctly. So for the experiment setup, you're going to go ahead and get the bar magnet that you used previously with lab 3, and you're going to go ahead and use a magnetometer in order to determine the north pole on the bar magnet, and go ahead and mark this. Then you're going to go ahead and take your aluminum foil, and you're going to hold the tube vertically, and you're going to position the magnet over the opening with the north side facing down. Then you're going to go ahead and film the drop, and you're going to find the time whenever the magnet exits the other side using the timestamp from the video. And then you're going to repeat this a couple of times. And once I repeated this about 4 times and took an average, I got about 1.18 seconds. And then the measurements that I got were the length of the tube, I got to be 0.31 meters. The width of the tube, I got 0.006. The inner radius, I got 0.002. And the outer radius, I got 0.026. And then U, which is the magnetic dipole moment, I went ahead and reused from lab 3, which I found to be roughly about 3.24. So a couple checkpoint questions just to check the understanding before we go into the computational model is, why can't we use a ferrous tube, like a steel tube or something with some ferromagnetic material? And that's because this is going to create an induced magnetic field, which is going to basically just kind of muck up the entire process of it falling down. It's just going to create a interfering field. And the magnet is going to slow. And this is going to be significantly slower than just free falling through space. But from here, we're going to go into our computational model. So the first part was basically just recording all of your values, which is at the very top in step 1. Step 2 is basically creating a function to calculate the magnetic field of a bar magnet, which I went ahead and reused code from lab 3. And then the next part is basically calculating magnetic flux, which is going to be go ahead and just having a magnet and then the ring. We're going to go ahead and get the ring radius, the distance, the speed, and you're just going to go ahead and apply the flux calculation in order to actually see everything. And then from there, we're going to go ahead and compute the typical B field at each ring. And then we're going to go ahead and just go through that entire part. And then we're going to go ahead and get the total force acting on the magnet, which is going to be the gravitational force as well as the magnetic force. And then we're going to go ahead and basically update the magnet's velocity and position by applying Newton's second law. And then we're just going to go ahead and plot this. And so I took the liberty, because I can't record it, of taking basically 3 kind of moments during this process. One as when it was about as high up as I could get it, and then that's on the far left. One about halfway through, which is in the middle, and one upon completion at the far right. And you can see that the total time it took was 1.302 seconds for it to drop. Now, the intensity on the coloring of the tubes indicates the magnitude of the current. However, the red and blue colors indicate opposite directions. So the color that corresponds to clockwise is red, and then the blue is counterclockwise. And we can go ahead and do that by basically looking at the change in the flux and looking at the induced current. And then what happens to the dynamics of the system when you flip the magnet around? Basically, it's still going to slow down, except what was previously a counterclockwise current is going to switch to a clockwise current, and vice versa. And then the total time into versus the real world is a lot longer, and the reason why that could be would just be that maybe my magnetic dipole moment was inaccurate, and so I could go ahead and change that, and I could calculate for each individual ring to try and get a more accurate time frame. And then the velocity versus time plot tells the forces acting on the bar magnet is initially gravity is stronger, then the magnetic force go ahead and supersedes it, and then they both get into steady state until it exits the tube and gravity takes over again. Then the resistivity, if it was approaching zero, the current would increase by just following V equals IR, where V is the EMF. And so if R drops due to the resistivity dropping, I has to increase, which means that overall there's going to be a lot of slowing. And if you cut holes into it, the flux will change. And so this would basically just kind of decrease the amount of flux, decreasing the amount of current, and actually increasing the fall time. And that's it for me. All right. Thank you guys so much.